Okay, so I'm going to be re-recording problems 11 through 20. We had a technical glitch where that part of the video got deleted, so now I get to do it again and get double the fun on these problems. So this won't be exactly the same as what I did during the sessions, but it'll be a reasonably close approximation and at least give you an idea of how to solve these problems. So the first one that I lost in the video catastrophe was the lattice energy problem, which is our favorite. So we're going to calculate the lattice energy for a hypothetical ionic compound M2X using the information given below. So when we talk about lattice energy, we're talking about this process here. So for M2X, it's the energy involved with forming the ionic compound as a solid, and we're forming that from gas phase ions. So in this case, we have 2 M pluses and X2 minus. Now, thinking about the questions that are going to be on the exam, it's going to be a combination of this type here where we're actually calculating the value for the lattice energy. So the lattice energy is the enthalpy change for this reaction. Or there's going to be conceptual questions where we have to compare lattice energies using the charge and the size of the ions. So there's some things there that you're going to want to review as well. But in terms of actually determining how to determining the lattice energy, we need to think about how to do this, and there's a general formula we can use that works, and I think is an easy way to do this, and will hopefully save you some time. So this is all based on Hess's law. It'll make more sense now, hopefully, that we've covered that section of the text, but there's still a lot of steps involved, and it's probably easiest to just remember this equation and use it, and I'll point out some of the caveats with this equation. So if we have an ionic compound that has this formula, M with some number M, and then X, which is the nonmetal, with N of that, so those are the subscripts in the chemical formula. This formula will apply that if our nonmetal X has a standard state of X2. So if X is a nonmetal like oxygen or any of the halogens would exist as X2, a diatomic, this equation will work. There's some examples with sulfur that are a little bit different, and I'll point those out here in a second, but for most things, if X is a nonmetal, it's going to exist as X2 in its standard state. And the reason this matters is because the first step, as I'll show you, involves the delta H formation. Formation enthalpies, as we've learned since then, are formation of a compound from its elements in their standard state. So the standard states of the elements will affect things here. So in this situation, our lattice energy then, we have 3 terms that are always the same no matter what type of compound it is. We're going to have the delta H of formation for the compound is the first term we're going to consider. So that's this one here, formation of the compound from its elements. And then we're going to subtract from that M times the delta H of sublimation. So sublimation is the conversion of solid metal into the gas phase metal. We've learned about that a little bit in chapter 9, and here's the sublimation enthalpy in this example. It's that term there. We're going to subtract M times the ionization energy of the metal. So if our metal's +1, it's just going to be 1 ionization energy. If our metal's +2, it's going to be a combination of the first 2 ionization energies, but either way we just put those in and multiply them by, again, the subscript for the metal, however many moles of that metal there are in the formula. So those 3 steps are always the same, and then we're going to have 2 additional steps that we add on for our nonmetal. So we have the dissociation enthalpy of our nonmetal, but we're going to multiply that by N over 2. So that's this value here. Remember, that's the enthalpy associated with breaking a bond. So in that case, it's going to be X2 going to 2 X's. And then we also are going to subtract N times the electron affinity. So that's the energy involved with our nonmetal gaining an electron and become an anion. So this is our electron affinity term here. And we have to put that in. It can be either 1 electron affinity if it's a X minus anion, or it can be a sum of 2 electron affinities, as is the case here. The sign of the electron affinity can vary, but we still want to subtract that value as we calculate our overall lattice enthalpy. Now the one step here that we're given, which we don't use, is the ionization energy of X. So ionization refers to removing electrons. We don't remove electrons from our nonmetal, so we don't want to include that step. So sometimes we'll give you extra information, so I don't think you have to use all of it. And here, these are the ones we want to use, and this is going to be the same terms that we have in just about all of these problems. Now, as I mentioned, there's a couple of exceptions. So if you have sulfur, remember that sulfur is S8 in its standard state. So this is going to be N over 8 instead of N over 2, because we want to just, we're just dissociating into 1 mole of sulfur. We don't want to include all 8 of them necessarily. And then the other thing is that our formation enthalpy needs to refer to 1 mole of compound. In its standard definition it does, but if we give you a formation equation that involves the formation of more than 1 mole of compound, you need to divide that, because this is a lattice energy per mole, so we also want to include a delta H formation that is for a single mole of compound. So with all those caveats in mind, for this one we can just plug in the numbers straight into this equation. So we have a formation enthalpy of minus 335 kilojoules per mole. We're going to subtract m times the delta H of sublimation. So our formula is m2x, so we need to have 2 of these in there, 2 times the sublimation enthalpy, which is 79 for this compound, minus 2 times the ionization energy for the metal, which is 525. And then for the nonmetal, we have n over 2. We only have 1x, so this is going to be minus 1/2 times the dissociation enthalpy, which is 178. And then minus 1, there's only 1x, so we use, again, just modify that by n, which is 1 times the electron affinity, which is a positive number in this case, because it's really a sum of 2, 123 kilojoules per mole. And so when we add up all these negative numbers, we get minus 1755 kilojoules per mole. Alright, so that's how we approach that problem. As I said, it's an application of Hess's law, but it's at least 5 different equations, and they're not the easiest to necessarily think about how to combine them. So my suggestion is to become familiar with this equation and how we use the different terms, and just practice these a bunch until you can do it really fast, because otherwise this will take quite a bit of time. So for number 12, we're going to talk about bonding types here. Which of the following compounds are matched correctly with their bonding type? And for bonding, we really only have 3 types in this course. So early on we introduced ionic and covalent bonding. Later on we talked about metallic bonding. So we need to understand those 3 types, and what compounds or what elements have those types of bonding involved. So the first one here, FeCl3. Sorry. Alright, let's let this do its thing. Okay, so FeCl3, when we're thinking about the type of bonding, we have to think about the types of elements that make up the compound. So this is a metal plus a nonmetal. So if we go to the periodic table, iron is right here, number 26. It's in the middle of the transition metals. So it's clearly in the metallic part of the periodic table. And then chlorine, which I should also point out, is over here, atomic number 17, clearly on the right side of the periodic table, so it's a nonmetal. So anytime we have a metal in combination with a nonmetal, it's going to be considered an ionic compound with ionic bonding. Okay, so anytime it's that combination, metal plus nonmetal, gives us ionic bonding. So this one's going to be correct. If we go to copper by itself, this is the one that we introduced most recently. So if you have a metal by itself, not paired up with a nonmetal, that's going to be a metallic bonding situation. And we also refer to that as a sea of electrons model. So remember that when you have metallic bonding, you have delocalized electrons moving around the surface of the metal, around it all, really through the entire structure, and it's a sea of electrons type of model, and we call that metallic bonding. So if it's just a metal, this is going to be the case here. There are compounds called alloys that have 2 different metals in them, which also exhibit metallic bonding. We didn't really talk about those, but if it's only metals, it's going to be metallic bonding. So this one's incorrect because copper would not be ionic bonding by itself. Number 3 is SOCl2. So we have sulfur, oxygen, and chlorine. We go to the periodic table. Sulfur, oxygen, and chlorine, all very clearly nonmetals. So whenever we have a compound that's a combination of nonmetals, all nonmetals, it's going to tell us we have covalent bonding. And then finally, so that one's correct. Then finally we have AlCl3. We've seen aluminum now in this review a few times. We know that aluminum is a metal. It's on the left side of the staircase here on the periodic table. The staircase runs down like this. Aluminum is just to the left of it. So aluminum is a metal. Chlorine, as we said, is a nonmetal. So even though aluminum is in the P block, it still technically is a metal, and we would still classify as bonding with chlorine as being ionic. So of these choices, 1 and 3 are correct, which leaves choice D is the correct answer. Alright, so number 13 is quite involved here. So we're looking on the basis of formal charges, which of the following is the best Lewis structure for the chlorite anion? First things first, let's make sure we have the formula correct for chlorite, because if we scan our answer choices, A through D are all ClO2, E is ClO3, so we should make sure we have the right formula. Chlorite, as it turns out, is ClO2 minus. So something that's going to review are the names and formulas of polyatomic ions. And there's one category in particular that can be a little bit tricky, and those are the chlorine-oxygen ions. So if you have, or the oxychlorides they're sometimes called. So you have ClO minus, you have ClO2 minus, ClO3 minus. So all of them have a -1 charge but different numbers of oxygen atoms, and they all have different names. Now these also can occur with other halogens besides chlorine, but the key parts of the name are when you have ClO minus, you have hypo at the beginning and then ITE at the end. So this would be hypochlorite. If it was bromine, it would be hypobromite. You have ClO2, which just has the ITE ending but no prefix. ClO3 has just the ATE ending, so that would be chlorate in this case. And then ClO4 minus has the per at the beginning and the ate at the end. So the ClO2 minus is chlorite. Remember, the same nomenclature applies to other halogens as well. Alright, so when we're evaluating Lewis structure, so that takes out choice E because this is the wrong formula. But whenever we're asked to evaluate Lewis structures, is this a valid Lewis structure? Is this the best Lewis structure? Whatever the case is, I think the best thing to do always is count electrons first. If your Lewis structure has the wrong number of electrons, it definitely cannot be correct. So let's just do that real quick for this. So chlorine is 7 valence electrons. So we go to the periodic table, it's atomic number 17, it's group 7A, so it has 7 valence electrons. There's 1 of them in chlorite. Oxygen is in the group next to chlorine, so it's in group 6A here, which means it has 6 valence electrons. So we have 2 oxygens, each with 6 valence electrons. And then finally we have a -1 charge. Whenever we have an additional charge, we add electrons. If it was a positive charge, we'd take some of these electrons away. So our total count for electrons is going to be 20. If we go through all of these structures A through D that we're still considering, A has 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. B has 20, C has 20. D, though, we have this odd electron here. If we count the total number of electrons in D, it's only 19. This has the wrong number of electrons, so it cannot be the correct formula. So choice D is out, just on the basis of having the wrong number of electrons. But now we need to evaluate A through C, and the only thing we have left to do here is octet rule and formal charges. All of these structures obey the octet rule, or in some cases they exceed it for the central atom, which is fine because chlorine is a heavier atom. It's it's below the second row, so we can do that. But we do need to think about formal charge. So remember that the way we calculate formal charge is it's the number of valence electrons. So we're going to calculate formal charge for every atom in the structure. So we look for number of valence electrons. We subtract the number of bonds that that atom is involved with, and then we subtract the number of non-bonding electrons, which we count individually. Okay, so basically what we're figuring out is we know how many valence electrons the atom itself has. We counted that at the beginning up here. And then we're asking, okay, how many electrons does that atom have when it's bonded in this structure here, and comparing the two and figuring out, is there a formal positive or negative charge, or is it in fact neutral? So if we do it for all the atoms in this structure, this oxygen here has a double bond, so it has 2 bonds, 4 non-bonding electrons. So a total of 6 electrons are surrounding this oxygen. It brought 6 into the compound. It has a neutral atom, so that's going to be 0. This oxygen is exactly the same, so it's 0. But then we have to figure out the central atom, the chlorine here. Chlorine has 4 bonds and 4 electrons around it, 4 non-bonding electrons. So a total of 8 electrons. Chlorine by itself has 7 valence electrons. This has 1 extra, which makes it a -1 formal charge. So this one has a -1 formal charge on chlorine. We have to have a minus formal charge somewhere, because another thing about formal charges is that their sum is equal to the overall charge of the molecular ion. So these are polyatomic ions that we're considering with a 1- charge. So we're going to have a -1 formal charge in that when we add all of them up. So that's what we get here. For this second structure here, this time the oxygens have single bonds. So if we have an oxygen with a single bond, we have 1 bond. We have a total of 6 non-bonding electrons. That's a total of 7. 6 minus 7 is -1. Both of the oxygens are the same, so they're both going to be -1. And then on the basis of the sum of the formal charges, or by counting it up individually, we have chlorine has 2 bonds, 4 electrons, a total of 6. 7 minus 6 is +1. Alright, sorry for that brief pause. I wanted to make sure that my tab was okay. Alright, and then going to this structure here, C, we evaluate formal charges. We saw above, if you have a double bonded oxygen that has 2 lone pairs of electrons, that has a 0 formal charge. An oxygen with a single bond and 3 lone pairs is -1. And then this chlorine here in the middle has 3 bonds and 4 non-bonding electrons, 7 total. 7 minus 7 is 0. Okay, so then finally we have to evaluate these structures and decide what is best. So when we're talking about formal charges, there's 2 things you want to do. We want to minimize the formal charges, in other words, have as few of them as possible, have as few of our atoms bearing formal charges as possible. So that's the first consideration, and choice B gets eliminated on those counts because it has 3 formal charges, 2 -1s and a +1. The other 2 only have 1 formal charge in the structure that's non-zero. But then in comparing A versus C, we have a choice. We can put our negative formal charge on the central atom, or we can put it on one of the oxygens on the outer atoms. If we're thinking about where to put negative formal charges, it's better to have them on the more electronegative atoms. Okay, so it's better to have a -1 formal charge on the more electronegative atom. Which in this case is oxygen. So that makes choice C our best choice. So typically if you have a negative formal charge, it's going to go on the outer atom. Sometimes it's unavoidable to have it on the central atom. If you have a choice, you want it on the outer atom. And then for positive formal charges, if you have a choice, it's better to have it on the central atom. Okay, so definitely review formal charges and how to evaluate structures using those considerations. So number 14 is a nomenclature question. So this one we're trying to find the best name for Al2S3. So when deciding how to name a compound, there's 2 basic sets of rules, one for ionic compounds, one for covalent compounds. We also learned acids. You'll want to review those as well. Those are a little bit different, but between ionic and covalent, we need to know the differences between how we name the compounds. So in this compound here, we have aluminum and sulfur. Aluminum, as we've already talked about, is a metal, and then sulfur is a nonmetal. So a metal in combination with a nonmetal means it's ionic compound, as we already talked about earlier. And then What that means is when we name ionic compounds, we don't want to have any prefixes. Alright, so we're going to put the cation first and then the anion. So we put aluminum as our cation. We don't modify its name at all. Now with the metal part of the formula, the cation, if it's a transition metal, we have to put the charge in parentheses as a Roman numeral. However, this one here, aluminum is in the P block. It can only form +3 cations. It loses the P electron and the 2 S electrons to make a +3, as we already covered earlier. So for aluminum or any other main group cation, including the ones in group 1 and group 2, those ones we don't need to indicate the charge. So this is just aluminum by itself. And then for the nonmetal, we put the root name sulf, and then we change the ending to IDE. Now the IDE ending occurs for both covalent and ionic compound. The big difference is that for doing a covalent compound, we would include prefixes which tell us how many of each atom we have. So you have an IDE ending on the anion in ionic compounds. It also appears in covalent compounds, but there's no, in this case, no prefixes. So aluminum sulfide is the correct name. So we don't want to include any prefixes, which would eliminate these two. This one has the wrong ending on the sulfur, and this one we don't put anything in parentheses after the anion, only after the cation if it's a transition metal. Now you should also be able to go the other way, which is taking the name of the compound and giving the formula. So if we were instead giving you aluminum sulfide and asking what is the formula for this, we have to know the charges of each cation, of the cation and anion. So aluminum, as we said, is always +3. Sulfur is -2. And then we have to balance the charge by having the correct number of each. So we can just cross over the charges and make them subscripts. And this gives us Al2S3. So if we want to take the name and find the formula, for ionic compounds we need to consider the charge of each ion, because in most cases the name doesn't tell us that directly. For covalent compounds it's a little more straightforward because we just use the the prefixes, the numerical prefixes, to tell us how many of each atom there are. Alright, so number 15 is asking which of the following molecules are linear. So to do this we need to draw the Lewis structure and then use VSEPR to figure out whether it's linear or not. If you only have 3 atoms in your compound, all of these do, CO2, H2O, xenon, XeF2, SO2, all of these only have 3 atoms. Your only choices are going to be linear or bent. So you don't have a lot of other you don't have any other options here, but we need to figure out which one is the case for these. So for CO2, we've drawn this structure many times. We have 4 valence electrons on carbon. Each oxygen has 6 valence electrons, so a total of 16 valence electrons. So when we draw these in, we get double bonds to oxygen. If we want to complete the octet on oxygen and on carbon, we need to have 2 double bonds in there, and we get this structure. Now the nice thing is, for determining geometry, if you're missing double bonds here and there, not a big deal. You just have to make sure that the number of bonds in lone pairs, or the number of bonded atoms in lone pairs around the central atom is correct. In other words, you have the correct AXE notation. This is AX2, so if you have AX2 with only 2 electron groups, you want to put them as far away from each other as possible, which puts them in a linear arrangement. The next one is H2O. We've also drawn the structure of this many times. So it's, as we saw before, it has 2 lone pairs on oxygen to complete its octet. And H2O is going to be AX2 E2. So there's 2 atoms and 2 lone pairs on the central oxygen, and that gives us a bent geometry. So this is derived from tetrahedral arrangement. So we have a tetrahedral electron group arrangement. The 2 atoms are then going to be at a bent angle relative to each other, close to 109.5, but a little bit smaller. So this one is linear, CO2 is linear, but H2O is not. And then if we go to xenon difluoride, XeF2, xenon has 8 valence electrons, each fluorine has 7, so we have 22 valence electrons to arrange in this structure. So when we draw it, we start with single bonds to fluorine and we complete the octet. Fluorine will only make single bonds if it wants to keep a 0 formal charge, so we don't want to draw any double bonds here. But after completing the octet on fluorine, we've only used 16 of our 22 electrons. We have a total of 8 electrons on each fluorine, 2 of them, so we've used up 16, which means the rest of our 22, which 6 more, have to go on the central atom. So this is going to give us an AX2 E3 arrangement. Now if you just remember that this is linear, that's fine, but to rationalize why is this linear, if we have 5 total electron groups, X2, E3, we're going to put those 5 electron groups in a trigonal bipyramidal arrangement. So we have a triangle in the middle, one above and one below. And whenever we have lone pairs with this electron group arrangement, all of the lone pairs go onto the central atom, around the central atom on the triangle. So the central atom lone pairs are all going to go there. We have 3 of them in this case, which leaves these 2 spots open for fluorines. These fluorines are sticking above and below the triangular plane. They're exactly 180 degrees apart, so this is in fact a linear geometry. Okay, so this one's linear. And then finally SO2 is our last one to consider. So SO2 has 6 valence electrons from sulfur, 6 from each of the oxygens, so a total of 18. When we draw the structure this time, we get, so if we start like this, we've used up 16 of our electrons, we have 2 more to go in the central atom. Now we can stop here and still predict the geometry just fine. However, a better structure for this is going to involve double bonds. So we want to complete the octet of our central atom, which right now is short, only has 6 electrons. So we're going to remove that lone pair and make a double bond, and then to remove the formal charges, we also want to do that a second time and get rid of another lone pair and make a double bond. So that's the best structure for SO2, but even without those double bonds, we would predict that it's AX2E, which is also a bent arrangement. So if you have one lone pair, it's always going to be bent. And in this case, it's going to be based on the trigonal planar arrangement, but with one lone pair, which gives a bent close to 120 degree bond angle. So this one's bent, so we're not going to count that. So the only linear ones are 1 and 3, which is choice D up here. Okay, so question 16 is a very related topic, which is which of the following has the greatest dipole moment. So if we're trying to decide if something has a dipole moment at all, it needs to be a polar molecule. So for a molecule to be polar, there has to be 2 things that's true. It has to have polar bonds, which means it has to have bonds where there's an electronegativity difference between the atoms. But also we have to take into account the shape. So, some molecular geometries give polar arrangements. Some of them are going to be nonpolar even if the bonds themselves are polar, so we have to take that into consideration. So there's a table in the notes, back when we covered this stuff, see if I can remember when it was. So somewhere around February 22nd, the notes from that section, we talked about VSEPR, and at the very end we talked about polarity. I didn't give you a lot of details, but there's a table in the notes from February 22nd that tells you which geometries are polar, which ones are nonpolar, assuming all of the outer atoms are the same. So that can help you if you just learn that table, but it's also usually something we can rationalize just by looking at the shape. So for all of these choices here in number 16, we need to figure out the shape of the molecule and then decide whether that gives us a polar or nonpolar arrangement overall. So for CCl4, we have 4 electrons on carbon, we have 7 each from the chlorine, so a total of 32 valence electrons. So for all of these, we're going to get a lot of practice drawing Lewis structures and determining molecular shapes. So for CCl4, we have 4 chlorines. We complete the octet on each of them. And so these are going to have all 8 electrons around each chlorine. We have a total of 4 times 8 is 32. So we have no more electrons for the central atom, which is always going to be the case with carbon as our central atom. No lone pairs there. So this is AX4, and all of the AX whatever structures, if there's no lone pairs involved, these are all going to be nonpolar. So AX4 gives you a tetrahedral arrangement, which it's not the most obvious one to consider, but tetrahedral compounds are nonpolar. And so this is one example of that. So this is a nonpolar compound, even though the bonds themselves are polar. There is an electronegativity difference, but in total the dipoles cancel out. So for P of 5, we also need to draw its structure. So this one's nonpolar. So that means it doesn't have a dipole moment, so it's not likely to have the greatest dipole moment out of all these. For Pf5, we have 5 valence electrons on phosphorus. We have 5 fluorines, each with 7, so a total of 40 electrons. When we draw the structure for this one, we start with single bonds to the fluorines, complete their octets, so we have 5 fluorines, each with 8 electrons. That's a total of 40. We've used up all of them, so we don't have any lone pairs in the central atom. That makes this AX5, and it's also a nonpolar geometry. So AX5, again, there's no lone pairs, that's going to be nonpolar. So this one's nonpolar. O2 is one we could have eliminated right off the bat because it doesn't have any polar bonds. Oxygen bonded to oxygen is a nonpolar bond. It's the same atom, same electronegativity. So this is going to definitely be nonpolar. So let's now evaluate the last two, xenon tetrafluoride. We saw xenon difluoride in the last one. So with 4 fluorines now, we have 8 valence electrons on our center. We have 4 times 7 from fluorines, a total of 36 valence electrons. So when we put these around our central atom, we're going to start with single bonds and complete octets to all of our fluorines. And when we've done that, we've used up 32 of our electrons. 4 times 8 is 32. We have 4 more that go in the central atom. So this is an AX4 E2 geometry. This isn't the most common one, so we might have to think about it a little bit. We have a total of 6 electron groups, so they're going to go in an octahedron around our central atom. So an octahedron is a square with one pointing up and one pointing down, similar to the trigonal bipyramidal, just with a square instead of a triangle in the middle. When we have lone pairs involved, we want to put them as far away from each other as possible. So one lone pair is going to go on top, one's going to go on the bottom. That puts them 180 apart, and then the fluorines are going to be then on the corners of our square. So when you have a square planar arrangement, you're going to have dipoles in each direction, but they're all going to cancel out. So each xenon-fluorine bond is going to have a dipole, but it's going to be completely opposed by a dipole that's 180 degrees apart on all sides. So the dipoles all cancel out. So in a square planar arrangement, it's going to be nonpolar. Okay, so this is one of the few electron group arrangements, or one of the few geometries with lone pairs that is going to be nonpolar. There aren't many, but this is one of them. And then finally, AX3E is the last one, so let's draw the structure for that. I let the cat out of the bag early. But the last one is NF3. So NF3, we have 5 electrons from nitrogen, 3 times 7 from fluorine, is a total of 26 valence electrons. So when we draw this out, you complete the octets on fluorine, the single bonds, as we always start with. So that's 24 of our 26 electrons. The last 2 go on the central atom. That gives us AX3E, and any geometry with one lone pair is going to be polar. So if there's only one lone pair, you have nothing to even think about, and so NF3 is going to be the only polar molecule of these, and that's going to be the one that then has the greatest dipole moment. Now if you're comparing the polarity of 2 different polar molecules, in this case we only had one that was polar at all, but if it's 2 different molecules and they're both polar, which one has a greater dipole moment? That comes down to electronegativity differences. To make that comparison, it's really, you need to have the same basic geometry. If the shapes of the molecules are way different, then comparing their polarities becomes very difficult. But if it's 2 molecules with the same shape, then the difference in electronegativity is going to determine which one is more polar or less polar. Okay, so on to number 17. How many sigma bonds are there in acetic acid, CH3COOH? So whenever we're asked to count sigma and pi bonds, we have to remember, what what kind of bonds are sigma, what kind of bonds are pi. It's pretty simple to remember what's going on here. So if we have a single bond, that will always be sigma. Now this is true using the valence bond approach. We saw in molecular orbital theory, if you're talking about simple diatomics and drawing MO diagrams, it's possible to have a single bond that is a pi bond. But when we're talking about valence bond theory for more complicated molecules, every single bond is sigma. And then for multiple bonds, double and triple bonds, they always have one sigma, and then the rest are going to be pi. So a double bond is 1 sigma, 1 pi. A triple bond is 1 sigma and 2 pi's. Okay, so for this one we need to draw acetic acid, CH3COOH. So we can take a little bit of a shortcut. If we have a compound with carbon, nitrogen, oxygen, and hydrogen, let's start by just drawing single bonds everywhere. So this carbon here is bonded to 3 hydrogens. The hydrogens can only have 1 bond. And then it's going to be bonded to the next carbon. And then whenever you see COOH, we're talking about this arrangement here. So it's an oxygen and then another oxygen with a hydrogen stuck on the end. So that's whenever you see this unit COOH, we're talking about that. Now we have to fill in some double bonds and lone pairs. In this problem it's not so important because we only care about sigma bonds, but if we want to also determine the number of pi bonds or the number of lone pairs, we should be able to do that as well. So there's some shortcuts we can take. If we have organic compounds, which are carbon, nitrogen, oxygen, and hydrogen as their primary constituents, there's some rules we can follow that will allow us to complete the octets and minimize formal charges, and we can draw the structure a little bit more a little bit more quickly than having to count all the electrons and go through all the steps like we normally do. So if you have carbon, it's going to want to have 4 bonds and 0 lone pairs. So all these are going to have 8 total valence electrons, but they're going to have different combinations of bonds and lone pairs. Nitrogen is going to be 3 bonds and 1 lone pair. Oxygen is going to be 2 of each. And then hydrogen, of course, is just going to have 1 bond and no lone pairs. Nothing else beyond that. When we say 4 bonds, 3 bonds, 2 bonds, that's any combination of single and multiple bonds. So carbon could form 4 single bonds, it could form 2 double bonds, it can form a double and 2 singles, a triple and a single. Any combination that adds up to 4 will work. And same with nitrogen and oxygen, any combination that adds up to 2 or 3 will work. So if we want to fill in the rest of this structure, this first carbon here already has 4 bonds, so we don't want to add any more bonds to it. This carbon only has 3 bonds, and this oxygen only has 1 bond, so they would be at benefit from having a double bond, which completes the octet of both of them, and then this oxygen should also have 2 lone pairs. This oxygen already has its 2 bonds, a single bond on each side, but we also add lone pairs if we want to really complete the structure. So that's the final Lewis structure for acetic acid. Now we can assign sigma bonds. So we have all of these single bonds are sigma. We have 1 double bond, which is a sigma, and 1 pi, and then we have sigma bonds here and here. So in total we have 7 sigma bonds. Okay. Alright, on to number 18, which is MO theory. Use molecular orbital theory to predict the bond order in the C2 2- anion. So for molecular orbital theory, what we're going to have to be able to do is draw the order of the orbitals. So molecular orbitals are when you take atomic orbitals and combine them mathematically, you form new molecular orbitals, which are then populated by all the valence electrons, and they're going to determine the type of bonding that you have in your compound. Now we're only going to do it for diatomics because otherwise it gets way more complicated. But there are 2 different diagrams we need to be familiar with for the p block elements. So if you have boron, carbon, or nitrogen, the first 3 elements in the p block, this is the order that you're going to follow. Sigma 2s. So whenever orbitals combine, they form bonding and non-bonding orbitals. So the 2 2s orbitals are going to combine to form a bonding sigma 2s and an anti-bonding sigma star 2s. And then the p orbitals combine to form both pi and sigma. So in the case of boron, carbon, and nitrogen, pi 2p comes first in the p level, then sigma 2p. So you have the 2 bonding levels. Pi is doubly degenerate. There's 2 orbitals at the same energy. And then the pi star comes next. So the anti-bonding are up top, and then the sigma star is last. Okay, so this is boron, carbon, and nitrogen. And then the other diagram that you want to be familiar with is oxygen, fluorine, and neon. So the bottom part looks identical, sigma 2s, sigma star 2s. But then at the p orbital level, we have a slight difference here. So here the sigma 2p comes first, then the pi 2p, and then the last two are still the same. So it's only these two center levels here that switch their order depending on what element we're talking about. So that's sort of what you have to remember. That's really important if we're counting unpaired electrons or deciding whether it's sigma or pi bonding. For determining bond order, which is what we're doing here, you can use the either diagram and it'll work out. So now that we have the correct diagram, we want to do C2 2-. So we have to count the valence electrons. So we have each carbon has 4, and then we have a 2- charge, which gives us 10 valence electrons. So we're going to use this diagram on the left, which is for carbon, and we're going to put 10 electrons into it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we use Hund's rule to fill them, or in the Aufbau principle, lowest to highest. Same rules as the filling atomic orbitals, and we get this arrangement. So the bond order then is going to be 1/2 times the number of bonding electrons minus the number of anti-bonding electrons, all in parentheses. Okay, so bonding electrons are those that are in bonding orbitals which don't have a star next to them. Anti-bonding electrons are ones that have a star next to them. So if we go to this one for C2 2-, we have 1/2 of our electrons. We have 2 down here, 4, 6, 8 of them are in bonding orbitals, and then only these 2 in the sigma star 2s are going to be anti-bonding. So out of our 10 electrons, 8 are bonding, 2 are anti-bonding, and that gives us a bond order of 3, which matches choice A. So for molecular orbital theory, you need to be able to populate the diagram and get the correct configuration, and then from that predict bond order and number of unpaired electrons, and then sort of what are the implications of those parameters. Okay, so that's a pretty standard MO theory problem, and we're going to, as I said, focus only on diatomics, and it's going to revolve around bond orders and unpaired electrons. Alright, so in this problem here, there's a typo that I should correct. The atomic mass of silver is 107.87. So what we're doing here is we have 2 isotope masses for silver. 107 silver has a mass of 106.905. 109 silver is 108.905. The atomic mass is 107.87. I messed that one up originally. And we want to know what is the percent abundance of 107 silver. Enter your answer in with 2 decimal places. Okay. So whenever we see atomic masses and isotope masses, remember that the atomic mass is the weighted average of all the isotope masses. So it's the fraction of each isotope times its mass, and we add all those together. Okay, so my video recorder hasn't died yet, that's good. So we have the atomic mass is going to be equal to the fractional abundance of each isotope times its mass, and we add all those terms together. So in this case we have 2 isotopes, 107 and 109. So our atomic mass is going to be the fractional abundance of 107 silver times its mass plus the fraction of 109 times its mass. Okay, so that's the equation, and we really have 2 unknowns here because we're trying to find the fraction for 107. We'll call that x. But we also don't know anything about the fraction for 109. So we have 2 unknowns, which means we need a second equation. So we want to write this out numerically. Our atomic mass is 107.87, and that's going to equal the fraction of 107, which is not x, times its mass. So we have 106.905x. And then the mass of 109 is 108.905, and that's going to be multiplied by y. And then the relationship between x and y, which are the 2 fractional abundances, is that x plus y equals 1. So the sum of all of the fractional abundances equals 1. And that means y equals 1 minus x. So we can substitute that back in for y and get us a new equation that only has x. So we're solving for x, which is the abundance of 107 silver. So 107.87 is going to be 106.905x plus 108.905 times 1 minus x. So x is the fractional abundance of 107 silver. And if we solve for that, we get 0.5175. Now remember, a fraction is a number between 0 and 1, which tells us sort of the ratio of that, that isotope to all the isotopes. But if we ask you for percent abundance, you have to multiply your fraction by 100. So don't be thrown off by when we say decimal format. Decimal format just means you need to have decimal places in your percentage to make it as precise as we need it. But it doesn't mean we just keep the fraction. So percent abundance always means multiply by 100. So the percent is the fraction times 100, which is 51.75%. Okay, so there's, for isotopes and for atomic mass and how those are related, there's really only one equation, this one that I wrote up top here, but know how to use it, and that we can ask for, we can have you solve for fractional abundances, we can have you solve for isotope masses, we can have you solve for atomic mass. Any of these terms in this equation could be your unknown. Alright, so for number 20, we want to know how many phosphorus atoms are found in 5 grams of calcium phosphate. Take the logarithm of your answer and report it to decibels. So I'm going to take a quick break here, and I'll come back. Okay, we're back. Number 20, how many phosphorus atoms are found in 5.00 grams of calcium phosphate? Okay, so this we're looking for the number of phosphorus atoms, so we need to know the chemical formula. So we have a compound here, and it could be helpful to know how many phosphorus atoms are in that compound. So to do this, we have calcium, which is a 2+ cation. So calcium over here is group 2A of the periodic table, so it's always going to be +2. Phosphate is one of our polyatomic ions. We need to know its formula, which is PO4 with a 3- charge. So we cross those over to balance charges, and we get Ca3 and then PO4 taken twice. So that's the correct formula for calcium phosphate. And what we're looking for is the number of phosphorus atoms, and we're starting with the mass of calcium phosphate. So the chemical formula here, Ca3PO4 taken twice, that can be interpreted in terms of moles. So there's 3 moles of calcium, 2 moles of phosphorus, 8 moles of oxygen, 4 times 2 is 8, per mole of compound, and that's going to be a helpful relationship for us. So if we have 5 grams of calcium phosphate, the first thing we want to do is convert to moles. So for that we need the molar mass, that simple mass to mole calculation that we've been using all semester now, or most of the semester anyway. So to get the molar mass of calcium phosphate, reminder that the molar mass is the sum of the atomic masses. We have 3 calciums, each of them is 40.08. We just look at the periodic table to get these numbers. We have 2 phosphoruses, which is going to be, each of them is 30.97. So phosphate is taken twice, so there's a total of 2 phosphoruses. And then for oxygen, we have 4 per phosphate, 2 phosphates, 4 times 2 is 8. And the atomic mass of oxygen is 16. So our molar mass for calcium phosphate is 310.18 grams per mole. So we're going to use that then to convert this mass of calcium phosphate into moles. So that gives us moles of calcium phosphate, but we're interested in the number of phosphorus atoms. So we have to figure out how many moles of phosphorus are in this. Remember, that comes from the chemical formula. PO4 taken twice, there's a total of 2 moles of phosphorus for every 1 mole of calcium phosphate. So let's take stock of our units. Grams cancel, moles of calcium phosphate. Now we have moles of phosphorus, but we want to know how many total phosphorus atoms there are. And this is where we use Avogadro's number, 6.02 times 10 to the 23rd. So this tells us that there are 6.022 times 10 to the 23rd units per mole. Here we're talking about phosphorus, so that'll tell us that there's that many phosphorus atoms in 1 mole of phosphorus. And so we multiply this out, we get 1.94 times 10 to the 22nd phosphorus atoms. And we want to report the log of this answer like we would in Blackboard. That's going to be the log of this number is 22.29. So this problem involved both mass to mole calculation and Avogadro's number. So those are both two concepts involving moles. We've used mass to mole a lot throughout the course. The one involving Avogadro's number, not as much, but both of those are important relationships involving moles. And then finally, the last one that I'll go over in this section of the video is number 21. We have a metal chloride with formula MCl3, which contains 35.62% chlorine by mass. What is the identity of M? Enter the symbol of correct capitalization. So this is a type of problem where we don't seem like we have a lot of information to start with. We have to figure out what is the identity of an unknown element. I would say in general, when you're asked to find an unknown element, compound, whatever the case is, it's helpful to find the molar mass, or in this case it's an atom to the atomic mass. So if we can find the atomic mass of our metal, M, we can identify what it is from the periodic table. And if we want to find atomic mass, we just need the mass of M in grams divided by the moles. So neither of these numbers are directly given to us. We have to figure out how do we get them. When we have a mass percent, so we're told that our compound is 35.62% chlorine. Whenever you're given a mass percent, it's helpful to assume 100 grams of compound. So if we have 100 grams of compound, that 35.62% tells us that we have 35.62 grams of chlorine, and then the rest of that 100 grams is going to be our metal, our unknown metal M, which is 64.38. So 100 minus 35.62 is 64.38. So in 100 grams of compound, we have those masses of chlorine in our metal. So we can assume that that's our mass for the metal for assuming 100 grams of compound. Now we need to determine how many moles of the metal are in that 100 grams of compound. And this we're going to get a little bit indirectly. So we don't know the identity of M right now, which we're trying to find. So we can't directly convert mass into moles because we don't know the atomic mass. However, we do know how much chlorine is in there, so we can use that relationship. The formula here is MCl3, which tells us we have 1 mole of metal for every 3 moles of chlorine. So if we know the moles of chlorine, we can figure out the moles of our metal. So if we have 35.62 grams of chlorine, we can convert that to moles because we know the atomic mass of chlorine, which is 35.45. And then our chemical formula tells us that we have 1 mole of M for every 3 moles of Cl, which means we have 0.3349 moles of our metal. So we have that 64.38 grams corresponds to 0.3349 moles. And if we divide the two, we'll get the atomic mass in grams per mole. And so we have to then go to the periodic table and figure out which element on the periodic table has an atomic mass close to 192.2. We search through the transition elements, which is where they are, and we get iridium is exactly 192.2. So our metal here is iridium. Alright, so that takes us through that problem. It's maybe a little bit hard to know how to get started on this one, but the relationships we used were both mass relationships and mole relationships. and we're able to then get the atomic mass of our unknown. All right, so to finish off this problem, we found that our atomic mass is 192.2. We go over to the periodic table, see if we can do that this time without destroying the system. There we go. Did my periodic table close too? Yes, everything closed. All right, so we go to the periodic table, and the element that's closest to 192.2 or exactly is iridium. So that's the identity of our unknown metal. Okay, so when you're doing problems like this, find the atomic mass, compare it to the periodic table, and then we'll have, that'll give you the answer. All right, so any questions on that one? Mostly just revolves around mole and mass relationships. Okay, 22 is talking about net ionic equations. So we need to know what is the net ionic equation when solutions of sodium hydroxide and iron 2 chloride are mixed together. So we write out the reactants. We have sodium hydroxide, NaOH. We have iron chloride. So we're mixing solutions of both of these. So both of these are aqueous solutions at the start. And then remember, the two possible products in an ion exchange reaction are just, we take the cations and the anions and swap them. So we have a sodium plus, which is going to compare with Cl minus to make NaCl. And then we have iron, which is in the 2 plus, has a 2 plus charge. There's 2 chlorides, so that means this has to be plus 2 to balance. So we have iron 2 plus, and it's going to combine with hydroxide, OH minus. So we're going to get FeOH2. So if we want to balance this, we need to have a 2 in front of here and a 2 in front of here to get it balanced. Okay, so this reaction is balanced. These are both aqueous solutions. Now we have to figure out solubility rules for our products. So NaCl is sodium plus and chloride. Sodium is always soluble, Na plus. So this will be aqueous, but then iron hydroxide, most hydroxides are insoluble. The exceptions are the group 1A, sodium, lithium, potassium, all those, and the heavier ones in group 2A. So hydroxide is usually insoluble, and that's going to be true for any transition metal hydroxide especially. So this one's insoluble, so it's going to exist as a solid. So then the next thing we do is we break up all the aqueous species into their ions. So if we do that, we get 2 Na plus. So sodium hydroxide is soluble, so it divides up into its ions. 2 OH minuses. Fe2 plus on the reactant side is dissolved. 2 Cl minuses. And then on the product side, we have still 2 Na pluses from sodium chloride, 2 Cl minuses also from that compound, and then we have FeOH2, which is still a solid. So this one is insoluble, so we don't break it up into individual cations and anions. So that's the total ionic equation. That takes everything that's soluble, breaks it up into ions. And then finally we have to remove the spectator ions. So spectator ions are the ones that appear on both sides of the equation. So Na plus is on both sides, Cl minus is on both sides as an aqueous ion. So we get rid of those, and our net ionic equation is finally just going to have Fe2 plus. Doesn't really matter what order we write them in, but usually we write cations first. 2 OH minuses going to FeOH2 as a solid. So when you're doing a precipitation reaction, the net ionic equation only has the ions that combine to make your insoluble product. And that's going to be this case here. So the one that matches that is choice C up here. Okay, so in the top one, we're not making, this is one of our reactants, so we don't want to count that. This one here is our, includes both products. We only include the insoluble, we remove the spectators. And that one also includes soluble compounds, and this one is the sort of the formula or molecular equation. Yes?
You said hydroxide is insoluble unless there's 2 exceptions. What were those again?
So the exceptions for hydroxides are all of group 1A. Remember, group 1A is always soluble no matter what it's paired with, so that would work there. And then calcium, strontium, barium, the heavier group 2A ones, are also exceptions. Okay, so all the transition metals, hydroxides, are going to be insoluble, as well as beryllium and magnesium, although those aren't very common ones, but they do exist. Okay, questions beyond that? All right, so familiarize yourself with the solubility rules. We haven't really used those since that chapter, but that wasn't all that long ago, so just take a little bit of time to reacquaint yourself. Okay, moving on to number 23. Calculate the molarity of perchlorate in a solution containing 3.58 grams of aluminum perchlorate dissolved in 125 milliliters of solution, and enter your answer in decimal format. So when we're doing molarity problems, remember we can define molarity for either the entire compound itself, or if it's an ionic compound, we can define the molarity of each individual ion, and that's what we're doing here. We want to know what's the concentration of just perchlorate. So to help us, we're going to need the formula for aluminum perchlorate. So as we've seen a few times already, aluminum is always +3. Perchlorate we've also seen before, that's ClO4 with a 1 minus charge. So that means the formula for this compound, we need to have 3 of our anions to balance charge. It's going to be AlCO4 taken 3 times. So in this compound, we have 3 perchlorate anions per formula unit, and that relationship is going to be important for this as well. So what we're looking for is the molarity of perchlorate. So we need the moles of perchlorate divided by the liters of solution. So that's the definition of molarity. So we need both of these quantities. Now we gave you the volume of solution right in the problem, 125 milliliters of solution. We have to convert that to liters to use it, but that can go right in here to the denominator. That's liters, not milliliters, sorry. Okay, so we have 0.125 liters of solution. For molarity, the volume has to be in liters to work out. And now we just need to put in the moles of perchlorate, and getting that is going to take a little bit of doing. So for moles of perchlorate, we know we have 3.58 grams of our compound. All right, so I gave you the formula mass, 325.32. So that means 1 mole of compound has a mass of 325.32 grams. Now this is where very many of you stop and don't do the next step. So this tells us moles of aluminum perchlorate, but we need to find moles of perchlorate ions individually. So you need to make sure you use that relationship that there's 3 moles of perchlorate per mole of compound. So don't forget that last step, because we're asking you specifically about the perchlorate ions. So there's 3 moles of perchlorate per 1 mole of aluminum perchlorate. So when we calculate that out, we get 0.0330 moles of perchlorate. Okay, so many of you forget to do this last step, so don't forget to do that this time. You have to make sure you account for the number of ions in the formula. So when we put that back up here in our molarity calculation, we get 0.264 molar. Okay, so the concentration of aluminum would be 3 times less than that, because there's only 1 aluminum for every 3 perchlorates. So make sure you look closely at what the question is asking you for. Which quantity do we want? In this case, it's the concentration of perchlorate by itself. Okay, questions on that one? Okay, finally, last one for this session. Balance the following redox reaction and give the sum of the coefficients. All right, so balancing redox reactions is another one that we introduced not too long ago, but haven't really seen it since then, so we need to review. So when we do this, the first thing we need to do is find the oxidation numbers. So we have to remember the rules for that. So for oxidation numbers, there's some that are very obvious. So hydrogen, if it's in a covalent compound, is going to be +1. Oxygen is almost always -2 unless it's bonded to itself, or fluorine. Fluorine is always -1. So look for some of the obvious ones, and that'll help you. So in HNO2, it's a nonmetal compound, so hydrogen is +1 and oxygen is -2. Okay, so it's in nonmetal compounds, that's going to be the case. And the sum of the oxidation numbers has to equal the charge on the compound. So HNO2 is a neutral compound. We have two -2s, we have a +1, so we need a +3 on nitrogen to balance that out. So the oxidation number of nitrogen is +3. H plus is an ion by itself, so that becomes just the charge of the ion, which is +1. So here's a difficult one here, dichromate CR2O7 2-. So oxygen, as always, is -2. We have an overall -2 charge. So we have 7 -2s is a -14. We need to have then 2 +6s to add up to -2. So again, you have a -2 charge that's going to be equal to 2 times chromium's oxidation state plus 7 times oxygen, which is -2. So that means each chromium has to be, +6 for that to work out. Okay, so there's we need a total of +12 on chromium. There's 2 of them, so each of them is +6. All right, so that's a slightly difficult one. We go to NO3-. In the product side, we have a -2 on oxygen. We have 3 -2s is a -6. We need a +5 on nitrogen to add up to -1. And then chromium +3 is an ion by itself, so that becomes +3. And then water, we have +1 and -2 for hydrogen and oxygen. All right, so water is always the same. So those are the oxidation numbers. Let's get rid of that to get it out of the way. And now we have to find the ones that are changing. So when we balance redox reactions, it's sort of a two-step process. The first step is to balance the number of electrons that are being transferred. We need to know the oxidation numbers to know which species are either losing or gaining electrons. Once we balance the electrons, then at the end we come back and balance out the number of atoms and make sure that all works out. So nitrogen here is going from +3 to +5. So that's a 2-electron process. Okay, so the oxidation number is changing by 2. It's getting bigger, so that means it's losing 2 electrons. And then our chromium is going from +6 to +3. Now remember here, we have to have at least 2 chromiums because each of these chromiums is +6, and then they're becoming +3 in the product. So we need to put a 2 out front to balance that, right off the bat. If the species which is changing its oxidation number, if there's an imbalance of them on either side of the equation, you need to keep that in mind. So we have 2 chromiums here. Each one is going from +6 to +3. So each one is changing by 3 electrons, but there's 2 of them, so it's a total of a 6-electron process. So going from dichromate to 2 chromium 3 pluses is a 6-electron process. We need this to also be 6 electrons. The number of electrons has to balance. So that means we need to have all of these coefficients multiplied by 3, the ones that involve nitrogen. So when we work that down, then we get 3 HNO2, so we need 3 of those to balance the electrons. We haven't balanced H plus yet, we'll save that for the end. We only want to have 1 CR2O7 2-. We need to have 3 nitrates because that's also involved in the electron transfer process. 2 chromium 3 pluses, we had to balance that right off the bat to get the chromiums correct, and then we have water. Okay. So once we've put coefficients here to balance number of electrons, we don't want to touch those anymore. So this we're not going to change, this we're not going to change, this we're not going to change, and this we're not going to change. So all of these things that we just balanced using the number of electrons, we don't want to adjust their coefficients anymore. But we still have H plus and water to worry about. So if we go to our reactant side, we have, let's balance oxygen. That's usually the first one to look at. So on the reactant side, we now have 13 oxygens. We have 2 each from nitrous acid with a coefficient of 3, so we have 6 plus 7 is 13 oxygens. On the product side, we have 9 from our nitrates. We need 4 more to balance oxygen, so we put a 4 in front of water. Okay, we don't want to touch the coefficient on nitrate because we already balanced that to get the number of electrons right. And if we add 4 more waters, our oxygen is balanced. And then if we look at hydrogen, we have 8 on the product side. We have 3 here from HNO2, so we need to have 5 more from H plus to balance hydrogen. So the last steps are just using inspection to balance the things that don't get involved in the oxidation or reduction process. Usually those are things like H plus, water, maybe some simple ions, that could be involved as well. But for those, we balance them just by inspection. So now the question here is asking for the sum of the coefficients. So we have a 3 in front of HNO2, a 5 in front of H plus. Remember that if there's no coefficient, that means it's 1. We have a 3 in front of nitrate, a 2 in front of chromium, 3 plus, a 4 in front of water. So if I added those correctly, that's a sum of 18. Okay, so the sum of all the coefficients is 18. So in redox reactions, you very often have big coefficients, and you need to balance electrons first.
What's that called? The oxidizing agent?
All right, so the oxidizing agent is the one where the oxidation number decreases during the reaction. So the oxidizing agent would be this one here, which is dichromate, and the other one will be the reducing agent. Okay, so that's also an important consideration. In terms of the videos, since we had that technical glitch, I'll re-record those problems that we missed, but I'll either combine them with ones at the end, or I might have 2 separate videos from this session as well. So just be on the lookout for that. I'll try to clearly mark what's in each video, and I will see you guys on Monday.
Was this one because there was only one X?
Yeah.
So if it was 3, would it be a 3 over here?
Yeah, I don't think we're going to have 3s. It's going to be either 1 or 2. But yeah, if there's something other than 1, you have to multiply that by that number.
Okay, and then same goes for the half. Would it be 1 over whatever the number is for X?
Yeah, so for 2 x's, it's n over 2. So it'd be, if there's 1, it's going to be 1/2. If there's 2, it's going to be just 1.
Oh, okay, got it. Thank you.
Hey.
Why did you go for 3 again?
So this is 6 electrons going from 2 chromium plus 6s to 2 chromium plus 3s.
Okay.
This is only 2 electrons going from a plus 3 to a plus 3, plus 5. So they need to be equal. So you have to adjust one or both of those coefficients to make sure the number of electrons is equal. So if we multiply these coefficients by 3, we now have 3 things that are each losing 2 electrons for a total of 6.
So you just use it from the chromium. You just use that one.
If there's a different, if there's an imbalance,
and you could just multiply.
sometimes you have to multiply both of them. So if one of them is 2 and one of them is 3,
Yeah.
you multiply one by 3 and the other one by 2 to make it 6 each. So you just need to find
Just
the lowest
to get-
common,
okay.
the lowest multiple that makes them both the same.
Got it. Thank you.
Yep.
We went over this yesterday, but I kind of forgot. So originally chromium has 6, and then it goes